is Marsel Faizullin, and I'm a PhD student at Mobile Robotics Lab, Skoltech, Moscow. And I'm really glad to participate in this great conference, and would like to present our work called Best Access Composition, Multiple Gyroscopes IMU Sensor Fusion to Reduce Systematic Error. First of all, let me briefly describe sensor model, IMU sensor model for tasks, for example, visual inertial odometry. In addition to real measurements, IMU sensor model, classical IMU sensor model, introduce random noise and smooth bias, slowly varying bias into this model. And our work here is to work with multiple inertial measurement units, specifically to improve accuracy of estimated orientation by our specific tasks. This IMU sensor model is classical thing that we will talk about later. So if we are talking about multiple IMUs, the so-called average virtual IMU, where sensor measurements from real IMUs is just averaged with proper transformation to get our virtual measurements that may put into visual inertial odometry. For example, state-of-the-art works related to these approaches, maybe as example as Jenga tool. They derive concise but really detailed theory on multiple IMU sensor fusion and create their own platform, visual inertial platform, and introduce their 9 IMU board, and they test this platform and state that their approach improve accuracy of position for about 25%. And this is really elegant and simple theory introducing classical IMUs, but it cannot obtain entire potential for real chip IMUs because of systematic errors. These systematic errors are not preserved in this simple classical model. This can be nonlinearities, dependence on dynamics, non-Gaussian distributions, etc. And in order to tackle the problem of systematic errors, we introduce this proposition. We utilize not, first of all, we measure this systematic error for different subset of IMUs and utilize not all of IMU measurements, but only some part of them. For example, in this figure, you see multiple IMUs, and for some period of time tau, we just utilize z-axis measurements from IMU2, y-axis from IMU3, and x-axis from IMU4. And for other period of time tau, we utilize some other different subset for state estimation. The question is how to implement this. This is two steps approach, but first of all, zero step is IMU's calibration in order to gather relative orientation between real sensors and our virtual IMU. And during calibrations, also scaling and misalignments are provided because we have cheap non-perfect IMUs. First step is in our approach is to measure error of state estimation with different subsets of IMUs of access. Sorry, we measure this error by comparing state estimated by visual data by camera and state estimated by different subsets of axis of IMU. For example, we utilize 5 frames of visual camera in order to get poses from it and poses from our virtual IMU. In this example of 2 IMUs, we have 8 subsets, and at this case we have the lowest error for subset x-axis from the first IMU, y and z-axis from the second IMU. And the next step is to somehow transform these measurements in order to properly utilize these measurements as virtual IMU. So this is some matrix A to provide these virtual measurements. If we do not provide this proper transformation, we will see discontinuity between different subsets measurements. For example, if you stack measurements from one subset, from the second subset, we will see this discontinuity, and we want to avoid this. And the proper transformation is can be found easily because of previous calibration of our sensors. Here, this found matrix is just composed from rows of different calibration notation matrices. And this matrix is invertible if heterogeneous axes of different IMUs are coplanar. This can be we can provide this invertibility, but just by orienting our IMUs in the same direction, just by eye. That's more than enough to be this matrix invertible. And what else? It's actually it, and we just need to repeat step 1 and step 2 for every these tau seconds, for every period tau. For justification of our approach, we developed our own visual inertial platform with 3 IMUs and single visual camera. And we utilize April text array for 2 tasks. First of them is visual odometry. Visual odometer, it's how to explain this? We utilize this as emulator of real visual camera because we are working mostly on IMUs, not with visual data. And the second task of April text array is ground truth data for different stage in our experiments, and I will explain them a little later. And we just recorded several minutes video, divided this into 44 tracks, and try to get statistics on improvements by our approach. And I would notice that there is no mix between ground truth and visual data in our experiments, that it's correct in our work. Now it's...
Marcel, you have a few minutes left, so you come to conclusions.
Yes, it's final slide. We evaluated our approach by 2 stages. If you can see in the left graph, we have stage 1. It's from -4 to 0 seconds, where we utilize visual and inertial data for state estimation. And in the end of this stage, we just our approach trying to choose the best axis, and with this best axis we provide state estimation in open loop. We also trying to estimate state in open loop with single IMUs and our baseline average virtual IMU. And in the right top corner, you can see the results. We have up to 20% improvement during 2.5 seconds. Comparing to our baseline, it's averaged virtual IMU. You can see this red line. And even with 2 IMUs, we have better accuracy in open loop, comparing this with baseline. It's yellow line. And the third graph here in the bottom is that this approach utilizes every axis of every IMU, And by this, we assume that our approach, looking at these systematic errors and trying to be better than just observing random errors. And here we also imply that systematic errors are not predictable and non-stationary. Actually, that's it for my presentation, and I'm glad to answer your question. Thank you.
Okay, thank you very much. So we have time just for one question. Just raise your hand if you would like to pose a question to Marcel. I have one question. So what do you think is the most promising advance to your system? So what would you like to do next to improve even more your system?
Yes, I see. This path is clear. We are working on to implementation of this approach into visual inertial odometry algorithms.
Okay. Okay.